key skill central to the understanding of functions and calculus is the ability to sketch a derivative function given an original function, and vice versa. We have three examples here of functions, and we have to sketch their derivatives. So what we're looking at when we sketch derivatives is the points on the graph where the gradient is 0. So if we focus on those, they are the stationary points that I've just indicated. If we match those up with the derivative function, what we know is that the gradient of the tangent to this curve at a stationary point is 0. If I draw in a tangent, okay, touching the curve there, we can see that its gradient is 0. So once I've done that, each of these points on the graph of the derivative passes through the x-axis. Through this region here, the graph is decreasing. So in the graph of the derivative will be below the x-axis. Through this region here, the function is increasing. So in the graph of the derivative, it will be above the x-axis. Now the function decreases again, below the x-axis, and then it increases again, above the x-axis, in the graph of the derivative. So in order to make that work, the derivative function has to start in this region here, pass into the positive region, then pass into the negative, then into the positive. The way to make that work is like so. The size of those turning points doesn't matter so much, it's the shape of the curve. The other thing you'll notice is that there is a point here where the graph is at its most positive, and that corresponds here with a point of inflection, where the graph is at its steepest and most positive. Another one of those occurs there, when the graph is at its steepest and most negative in that region. In the second example, we don't have a stationary point, but we can split the graph using that point where the functions change. So this is a continuous curve here. This is a piecewise function. And so we split it at the intersection of the functions, or where one function ceases its domain and the other begins. So there are two things going on here. There are two straight lines, and this is going to look very different to the first example. As we look through here, that gradient, unlike the first one, is constant. Because it's constant and increasing, it has to be above the axis here, and it's not going to change. So it is always the same positive value. When we look through here, this isn't a stationary point, this is a line with a gradient of 0, and so its derivative is always going to be 0. So they are both horizontal lines in the derivative. One is positive, one goes through 0. If we had a region that went negative, then we would have a constant negative gradient, as shown there. Now the last one isn't a piecewise function, but it does have some key features that we need to consider. And the first is that there is an asymptote at x equals 0, and another asymptote here. Asymptotes present in the original function will be present in the derivative. As we look at this section, the function is always increasing, and so through there it's going to be above the axis. So we also have this asymptote along the x-axis at y equals 0, and that will also be present here. And that makes sense. This gradient in this region here is always positive. It never becomes 0. And as we go along this way, it's getting steeper and steeper. So when we draw the derivative, it's going to look pretty much the same. It's going to get steeper and steeper and steeper. And as we approach x equals negative infinity, the gradient is going to approach 0 but never reach 0. Skipping the middle section for a moment and looking at this section, as we can see, the graph is always decreasing. And so what we're going to have is it existing only below the x-axis. What it's doing is starting off very, very negative and getting less and less negative and approaching 0. So we've got that kind of shape occurring, only in reverse. Finally, if we consider the middle section here, we have a turning point. So that point there on the derivative will be x equals 0. Note that the asymptotes are at the extremities of the graph. Okay, we don't worry about the asymptote there. Horizontal asymptotes do not have to exist through the whole graph. So, considering each side of this, here it's increasing, so it will exist above the axis, and here it's decreasing, so the derivative will exist below the x-axis. So the only way to make that work, because it's getting more and more negative as we move away, is for it to do that, and then to do that. Alright, so this point is not very negative, this point is more negative. And it's getting steeper and steeper and steeper. Consider the same functions, or the same shaped graphs, but this time they are derivatives, and we have to sketch an original function. So this time, going in reverse, what we want to look at on the derivative is all the times where the derivative function, okay, this is now f dash x, all the locations where it is 0. We're going to match those up. And what we're going to do is look at where the derivative function is. So here, the derivative function is above the x-axis. So the original function is increasing. Here, it's below the axis. So the original function is decreasing. And then it's below the axis again. So the original function decreases yet again. And then it's above. And so the original function is increasing. So if we sketch that, what we have is a function that increases, hits 0, decreases, hits 0, decreases, hits 0, increases. And you can just extend those extremities a little. In the next example, again, I'm going to split the piecewise function at the change in domain. And what we have here is a graph that is always negative, but getting less negative. So through this region, it is doing something like that. But it doesn't reach zero. And then we have a graph that is always negative with a constant negative gradient. And so that is going to look something like that. There is nothing to suggest that these are or aren't continuous. So this and this would give us the same derivative. Similarly, if we look back at the first example, this will give me the same derivative. We do not know where the graph sits vertically when we do the derivative, do the original from the derivative function. And that's because we don't have a point fixing it. So any functions that are vertical translations of each other will produce the same derivative. This has no stationary points. I do want to split up the asymptotes again because asymptotes in the derivative will also be asymptotes in the original function. And what we have here is a positive gradient always, a positive gradient always, starting off not very positive, and getting more and more positive, starting off very, very positive and getting less and less positive. So essentially the same. And then here we have a function that is always decreasing and never hits zero. So the only way for that to work and for it not to cross the asymptote is to do that. So there is a point of inflection there, but it doesn't become zero.